Good morning and welcome to your final lesson for the term, absolute value graphs. These are variations of the standard form. So you might remember in the previous lesson we looked at normal straight line sketching, where the graph either had a positive straight line shape like that, or it had a negative straight line shape like that. Today we're going to look at when the actual format of the equation is not in standard form, nor can you write it in standard form in any easy way. Well, you can't at all, because of the fact that there's a variable outside of the absolute. So what we're going to be looking at is this definition. Remember that if the absolute of x is given, then that equals positive x if x is greater than or equal to 0, and it equals negative x if x is less than 0. Right, so keeping this in mind, we're going to apply that definition to this particular problem here. So firstly, we're going to say that if the value inside, which is 2 minus x, is greater than or equal to 0, then that means negative x is greater than or equal to negative 2, which means x is less than or equal to positive 2. Okay, so then let's work out what the straight line equation would be. That would mean that y is equal to 2 minus x plus 3x plus 2. Now let's simplify that into standard form. Normal straight line standard form. So negative x plus 3x is positive 2x, and 2 plus 2 is 4. Right, so we have, this is the arm of the absolute when x is less than or equal to 2. Then secondly, we have to consider the condition that if the inside of the absolute is less than 0, then we have negative x, which is less than negative 2, which means x is greater than positive 2. So for that condition, we would now make the inside of the absolute negative. So we, in effect, multiply negative into it. All right, so then we'd get y is equal to negative 2 plus x plus 3x plus 2. Right, and again, put that in standard form. So we have positive y equals x plus 3x is 4x. And the 2's cancel. Right, so we've got that straight line for when x is greater than 2. Right, so let's look first at the sketch of this. So we know then that the y-intercept of this would be positive 4, because that's the c value. So we know that the y-intercept, let's write that down, is equal to positive 4. And for the x-intercept, we let y equal 0. Right, so we get 0 equals 2x plus 4, therefore x equals negative 2. Okay, so let's plot these two to start with. So we're looking at this y-intercept of 4 and this x-intercept of negative 2. Right, so if we go to our Cartesian plane, make this a little bit bigger, we can then plot that we have an x-intercept of negative 2, and we have a y-intercept of 4. Right, so then this section of the graph would look like that. Okay, so that would be the y equals 2x plus 4. Now, obviously, normally you're drawing in pencil, but particularly draw this in pencil because you're going to erase part of it. All right, so but let's draw the other section of the graph first. So if we look back at the other section of the graph, we are looking at y equals 4x. And we know that goes through the origin because there's no constant. So we literally just have to work out one other point. So it's going through x and y, it's going through 0 on the x and the y axis. But if we say let x equal 2, for example, okay, so if x equals 2, then y equals 4 times 2, therefore y equals 8. So the other point we're going to plot is 2 and 8. Right, so we know the first point is going through the origin there, and the next point is going through 2 and 8 over there. Okay, so the next part of the function, I'm going to sketch in red just so that it's easier to differentiate, but just to go back to it, if we look over here, it's y equals 4x when x is greater than 2. So we've already plotted the point 2, 8. We know that it's going through the origin, so now we just need to link them. Okay, so to sketch it would look like that. And obviously, like I said, you're doing these in pencil because you're going to erase part of it. Okay, so to see which part we erase, we go back and look at the restriction. So let's look at the restriction for the blue graph first. And the blue graph said that we needed to have this function y equals 2x plus 4, the blue graph, when x is less than or equal to 2, which means that we need to erase the top part of the function. So that's got to go away because that's for when x is greater than or equal to 2. And then for the second line, the red line, that line is only valid, y equals 4x, when x is positive or greater than 2 at least. So we need to now erase the negative aspect of this line. So your final graph then would look like that. It's also quite important to label this point because that actually becomes the type of salient point, because that's where the graph changes direction. So here we would label this as 2 and 8, and obviously any intercepts need to be labeled as well. Example 2, determine the equation of the graph of y equals a into absolute x minus p plus q if it has a salient point at 1 and 3 and a y-intercept of 5. Okay, so you might remember, and this is in standard form. Okay, so that's the first thing to notice. We've got a negative there. I mean, we have to manipulate that if it was a positive, but we'd normally give it to you in a negative form. And because it's in standard form, we know that P and Q is the salient point. So we can simply substitute those straight in. Okay, so the salient point in this case, which is 1 and 3, we can therefore say that y equals the a into the absolute of x minus 1 plus 3. Okay, so we partly the way there. Now we need to just simplify and at least solve for a. Okay, they've told us that there is a y-intercept at 5. That means that coordinate is 0 and 5. So we can substitute 0 and 5 into y. All right, so we would get 5 as the y value is equal to a into 0 minus 1 plus 3. Okay, so now this absolute falls away now because there's a constant in there, which means 0 minus 1 is negative 1, but it's the absolute, so it's just positive 1. All right, plus 3, which means that a equals 2. So the final equation is y is equal to 2 into the absolute of x minus 1 plus 3. Example 3, sketch f maps x onto absolute of x divided by x. So don't get confused with the notation. Remember, this is just a different form of expressing the equation as opposed to functional notation, but it means the same thing. All right, so again, it's a non-standard formula here, so we have to apply the definition. We shouldn't just draw this by inspection. All right, so firstly, there is a restriction here. As soon as you've got a fraction with variables in the denominator, there's a restriction. So x cannot equal 0 here. All right, let's apply the definition. Right, so firstly, if the inside of the absolute, in this case x, is greater than or equal to 0, then we have y equals x over x, which means y equals 1. Okay, so remember that is for that specific restriction. And then if x is less than 0, then we have y is equal to negative x over x, which means that y is equal to negative 1. And again, this is for this specific restriction. Okay, so in other words, what I'm saying is, in the first case, y is equal to 1 when x is greater than or equal to 0. Y is equal to negative 1 when x is less than 0. Right, so firstly, we're going to sketch y equals 1 for x is greater than or equal to 0. Now, we don't need to waste time by sketching the whole y equals 1 and erasing part of it, because we can see straight away what it's going to look like. In both cases, there are horizontal lines. Y equals 1 would go at the top here through the y-axis, and y equals negative 1 would go below the y-axis. Okay, so I've just made the axes a little bit bigger, so it's a bit clearer. But before we carry on, remember that we said that x at least cannot equal 0 in both cases, because in both cases it would make the fraction undefined. So we're going to start by putting an open dot at positive 1 on the y-axis and at negative 1 on the x-axis. Okay, because that's implying that it can't equal 0. Right, so firstly, for the first one, if x is positive or greater than 0, then y equals 1. So that's the first one we're going to sketch. Right, so it's going to look like this, and it's going to go to positive infinity. Then for the next one, when y is negative 1, in other words, on this line, that is only valid if x is less than 0. So we're going to have a line that looks like that. And that'll also extend to negative infinity on the left-hand side. Right, in this case, example 4, y equals the absolute of x squared minus 1. Now, there are no other constants or negative signs outside the absolute. It is only one absolute expression, which means this graph can only ever be positive. In other words, it can only ever be above the x-axis. But it's useful to sketch the inside of the graph first for the purpose of this example, and also for neatness, because it's easier to actually reflect your negative part after the fact than to sketch it. Okay, so let's just sketch for now if the graph was just y equals x squared minus 1. All right, so we know this is a parabola that has a shape like this, x squared minus 1, going through 1 on the negative x-axis there. All right, so with that in mind, we just need to work out what our intercepts are going to be. So we can see that the y-intercept is going to be negative 1. And we can see that for the x-intercept, we have to equate to 0. You can probably work that out by inspection. So the y-intercept is negative 1. For the x-intercept, we're going to say let y equals 0. Therefore, 0 equals x squared minus 1. Therefore, x squared equals 1. So x equals plus minus 1. So the x-intercepts are at negative 1 and 0 and at 1 and 0. All right, let's sketch onto the Cartesian plane now. Right, I'm sketching in pink because we're sketching not the absolute yet, we're sketching the actual original parabola. So we know it has an x-intercept at negative 1, at positive 1, and at negative 1. Now remember, it's a sketch, so you don't need to be fully accurate. You need to be able to just sketch the intercepts of the axes and have the correct shape. All right, so there's the sketch of the original parabola. Now, because it's absolute, and I told you at the beginning that there's no negative on the outside here, there's no negatives over here, everything is positive, so there can be nothing below the x-axis. So when there's no constant or anything here, when there's no negative, all we need to do is reflect the negative part over the x-axis so that we get this. Okay, so you can see the negative y-intercept of negative 1 now becomes the positive intercept of y equals positive 1. And all these points reflected, their x values stayed the same, but their y values changed so that they were positive as opposed to negative. Okay, so now you'd see what I need to do actually now to tidy this up is the positive arms of the parabola are valid. So I'm going over them in blue so that it makes sense to you. And then on the negative side, we erase what is below the graph. Okay, so that your final function looks like this. So it still has the intercepts of positive 1 and negative 1, but in fact, instead of cutting the axis there, it actually turns on the axis there. Right, for the next section of the lesson, we're going to look at kind of what we did explore in the last example, but sketching graphs using reflections. In other words, not having to sketch each and every point and then erase and then reflect, etc. Although you can do that to a certain extent, but using our knowledge of what standard forms of graphs look like the parabola, like the hyperbola, the exponential graph, etc. Right, so this one, very similar to the previous one that we did. The function is the same inside the absolute, except now we've got a negative on the outside. That means, in effect, everything is negated from the previous question. So, again, let's just start quickly by drawing at least the graph of y equals the absolute value of x squared minus 1, because we've done that in the previous one. Okay, so remember, to sketch that, and I'm going to do it in pink, we would follow all the same rules that we did in the previous one, where we know that there's an intercept at negative 1, there's an intercept at positive 1, and then once we reflected it, we knew there was an intercept at positive 1. All right, so that's the graph that we would have got. But now if you look at the one they're wanting, there's a negative in the front, which means that the entire graph that we've sketched here has to now be reflected because everything now needs to be negative. Okay, because remember, the whole absolute can only ever be positive, but then once we reflect it, it'll all be negative on the x-axis. That means we're still going to have an x-intercept of negative 1 in blue now, and at positive 1, but now we'll have a y-intercept of negative 1. so that our new graph will look like this. Now, when they say by using reflections, they don't necessarily mean you have to draw what I've drawn in pink, but for now in the examples, it helps you to see where it comes from. You can, by intuition, draw the blue graph straight away. So I would say if you have drawn this part, you just need to erase it now. And you're only left with the graph that they've asked for. All right, example 6, f of x is equal to the absolute of 2 over x. Now, you should recognize this as a hyperbola. So if we look at the original function, so it would be y equals the absolute, not the absolute, sorry, but just y equals 2 over x. And if we look at our quadrant, that means that we would have the function in this quadrant and in that quadrant because it's positive. Okay, those are the two quadrants where y and x are both, y and x will combine to be positive. Remember, there are no intercepts here because the y-axis is an asymptote because there's no constant here, it's 0. And the x-axis is also an asymptote because there's no constant here, which makes the x-axis the asymptote. And because the fraction will be undefined if x is 0, it means that at x equals 0, in other words, the y-asymptote, there is also, the y-axis, there's also an asymptote. Okay, so if we had to sketch in pink roughly what this graph would look like, it would be in the first quadrant like this, and it would be in the third quadrant like that. Okay, that's the normal graph of y equals 2 over x. Okay, but instead, they're wanting the absolute. So like with example 4, everything that's below the x-axis needs to reflect above the x-axis. So in fact, if I take that one away now and reflect it above the x-axis, we get a function that looks like this. And in this side, it actually can also be blue because that side's valid. All right, so that now satisfies the absolute nature of the equation. All right, example 7, g of x is equal to the absolute of 2 to the power of x minus 2. So I'm going to start by drawing both of the original functions. Okay, so let's start in pink with y equals 2 to the power of x. Okay, now I'm just going to draw it roughly here. So y equals 2 to the power of x, we know that the y-intercept needs to be 1, because if x is 0, then 2 to the 0 is 1, so it means our graph will look like this, okay, going through positive 1. And then now in green, if I now had to look at what the graph of y equals 2 to the x minus 2 looks like, it would mean that the whole graph would shift down 2 units. So the asymptote, which was originally at y equals 0, will now move to y equals negative 2. All right, so that's negative 2. And our y-intercept that was positive 1 will also move down 2 units, so it'll go down to negative 1. So there's our y-intercept. So the graph then roughly looks like that. Okay, but now we have an x-intercept that we need to work out there. So in order to work out that x-intercept, we would let y equal 0. So if y equals 0, then we have 0 equals 2 to the x minus 2. Therefore, 2 to the x equals 2. So x equals 1. So we know that that value is 1. All right, now let's look at the absolute. Remember, it's saying that everything, because there's no negative here, because there's no constants here translating it up or down, the entire right-hand side is an absolute, which means whatever is negative needs to be reflected up. So in blue, let's see what's valid. Effectively, everything from the right of positive 1 is valid because it's already positive. So we know that that x-intercept of 1 is valid. What needs to reflect now is the y-intercept of negative 1 must reflect to positive 1. So we'll have a y-intercept there. Let's just draw this first part that we did first already. We know that it went up like that. Okay? Then secondly, this whole portion below effectively needs to reflect. The asymptote also reflects. So the asymptote is going to go to positive 2 on the y-axis. Right, so it'll look like that. Now just a word on the asymptotes. We can reflect the entire asymptote because the asymptote's not actually part of the sketched part of the function. So we don't get complicated and leave the negative asymptote where, etc. You reflect the whole, whatever asymptote was below the x-axis goes above the x-axis. And then now it's just a case of reflecting your original picture. So remember, instead of going down from 1, it's now going to go up through positive 1 on the x-axis and the y-axis to negative infinity. All right, last example, example 8. Sketch the f of x is equal to the absolute of 2 over x minus 2 using translations. Now, you may remember in a previous example, we did sketch this function of the absolute of 2 over x. All right, and then it looked like this. We had one branch there in the first quadrant and another branch here in the second quadrant. Now, all they're asking us to do here is to shift that original graph down by 2 units. So that means the original asymptote was here at y equals 0. It's now going to move down 2 units to y equals negative 2. So that new asymptote will be here. Right, then the pink section of the graph that I've drawn also all has to shift down 2 units. And so that means it's now going to intercept the x-axis, and we have to find out what that x-intercept is going to be. Now, we don't have to use the absolute to work that out because we know that this first branch here is true for the absolute of 2 over x and 2 over x as well. That's what it would look like. So we really just need to work to find the x-intercept. We need to work with the equation y equals 2 over x minus 2. And in order to find the x-intercept, we're going to let y equal 0. Right, so if y is 0, we have 0 is equal to 2 over x minus 2. Multiply everything through by x, then we get 0 equals 2 minus 2x. Right, take over the 2x, we get positive 2x equals 2, therefore x equals 1. So it means our x-intercept of the new function is going to be 1. Now, because the functions are symmetrical about the y-axis, it means that the x-intercept on the negative x-axis will be negative 1. And then from there, you can just draw them. But first, let's rather draw first. So we're going to draw the new graph, which will look like that. And then we can erase the pink section because that was the previous one without the absolute. All right, and then there you have your function. All right, thank you once again, girls, for really helping us this term to get through this work, and I really hope to see you next term. This is the exercise homework that you can do today. It's a continuation of exercise 2 on page 83, C, D, E, and F, and I'll post the memos to these on Wednesday.